Okay, let's talk a little bit about scientific notation. Scientific notation is a way of writing numbers, particularly measured numbers, but I guess it could be any number, um, in the form of using a number which is between 1 and 10, and then that number multiplied by some power of 10, 10 to the x. So 10 to the 2, 10 to the 6, 10 to the minus 5, what have you. Uh, let's take a look at how this works. Take a look at a few examples. So 231, we could rewrite 231. If we want to write this number here as a number between 1 and 10, write this as 231 times 100. And because 100 is 10 to the 2, we could then rewrite this as 2.31 times 10 to the 2. Okay. Similarly, let's see, 87 million, right? If we want to rewrite this as a number between 1 and 10, this is the number that we're going to work with. So we can write that as 8.7, and 87 million is the same as 87 times 10 million, and 10 million is 10 to the 7th, so we can rewrite this as 8.7 times 10 to the 7. And you can do the same thing for numbers that are smaller than 1. So 0.00631, we can rewrite this as 6.31 times 1/1000th. So times 0.001, and 0.001 is 10 to the minus 3. So we can write the number like that, 6.31 times 10 to the minus 3. Now notice also when we change these numbers to a number between 1 and 10, we have to move the decimal over a couple of spots right here. So in the case of 231, we move the decimal over 2 spots, and notice we've got a 2 over here. The exponent of the 10 is a 2. In 87 million, we have to move the decimal over. I'm going to go in little jumps, 3 spots, 6 spots, and then one more, 7 spots, and our exponent is a 7. For numbers that are less than 1, in order to write this first number, we have to move the decimal in the other direction. So in this case, we're moving the decimal over 1, 2, 3 spots, and our exponent over here is -3. Okay, so the number of spots that you move the decimal is the same. This exponent number is the same as the number of spots that you're moving the decimal, and whether that exponent is positive or negative depends on whether the original number is larger or smaller than 1. Okay, so why do we do this? Why bother to rewrite numbers that way? There are actually several really important reasons to use scientific notation. Right? One of the simplest ones is it just makes things easier to look at. Right? If you had a number like 890 million, right? That just takes up a lot of space, and it's a lot easier to just write 8.9 times 10 to the 8th, right? It's just a little bit more compact, right? And that can be really helpful, particularly if you're working in spreadsheets or something like that, where all the numbers have to fit into a cell. It can be ridiculous trying to get numbers like this to fit into a cell. But if you put them all into scientific notation, then it's a lot easier to deal with. One of the other reasons is that it helps eliminate errors when you're trying to count zeros, right? Have you ever been taking a test and you put something in your calculator and you've got like something like 0.0000039, and then there's some second step and you've got to type that number in, or you've got to transpose that number onto your exam paper. You got to write the number down, and I see a lot of people looking at their calculators and they use a little tip of their pencil to kind of count, okay, 1, 2, 3, 4, 5 zeros, and then when you write the number down on your paper, you're trying to copy that down and make sure you put in the right number of zeros. It's really confusing, and it's really easy to make mistakes when you're trying to count all of those zeros. Whereas if you just write this number as 3.9 times 10 to the minus 6, then you don't have to do any counting. This is a lot more clear than this is over here, and you don't have to worry about zero counting. And the third reason, this maybe is the most important reason, is that it makes the precision of measured values explicit. Right? Remember last time in the video on significant figures, we had an elephant that weighed 9,500 pounds. Right? And we said that typically when we see a number like this, we would assume that this is the last significant figure, this 5, right? And so the error or the imprecision would be in the 100ths place. But that might not be the case. It could be that the measurement was measured precisely all the way out to the tens place, or that it was measured precisely all the way out to the ones place, right? Or possibly even further than that. So, but the way that the number is written, it's ambiguous. You can't tell whether this is supposed to be interpreted as 2 significant figures, 3 significant figures, or 4 significant figures. The nice thing about scientific notation is it gives you options on how you want to write this number. And so we could write this number as 9.5 times 10 to the 3, which clearly has 2 significant figures. We could write it as 9.50 times 10 to the 3, or 9.500 times 10 to the 3, and so on and so forth. So whenever we write a number like this number here these are the significant figures over on the left. Oops, I put my little bracket in the wrong spot. I didn't need to do that. Okay, so those are your significant figures, right? And remember, when we talked about zeros, the only reason to put a 0 over on the right like that is to indicate that that is part of the measured value, right? Because 9.5, 9.50, and 9.500 all mean the same thing. The only reason that anyone would bother to write these extra zeros here is if they were actually part of the measurement. So the zeros in that case are significant zeros. In fact, that kind of goes to the other thing. If you think back to the lecture on significant figures, we said all non-zero digits are significant, and zeros are significant if they're part of the measured value, and they're insignificant if the zeros are there only to help you locate the decimal place. Right? So that's why this makes things a little bit easier, because the decimal place, the position of the decimal place is indicated by this exponent right here, right? The 10 to the 3. Excuse me, I'm sorry about this. I didn't realize there's not supposed to be a negative sign there. All right, so all of these are 10 to the positive 3. I don't know why I had a negative. Anyway, as I was saying, the position of the decimal is indicated by this 10 and the exponent. So you don't need to use zeros to indicate the decimal. So when you're using scientific notation, all of the digits over on this side are always going to be significant figures. So it's really easy to figure out what are significant digits and what aren't. Okay, let's try some practice here. Take each one of these numbers, each one of these measured values, let's say, and convert it to scientific notation. And as you convert it to scientific notation, try to retain the same number of significant figures as we have in the original number here. Okay. All right, go ahead and hit the pause button, write all of these down, then rewrite them in scientific notation, and then unpause, and I'll show you my answers. All right, so the first one, 173.6. If we want to change this to a number between 1 and 10, we get 100 or 1.736, right? And that's 1.736 times 10 to the, or excuse me, times 100, which is 10 to the 2, right? You can also see that because we need to move the decimal over 2 spots. So this has got to be 10 to the 2. And let's make sure we keep our units in there. Okay, 150 milliliters. That's also 2 spots. So this is 1.5 times 10 to the 2 milliliters. Okay. And here we're making a little bit of an assumption, because remember, when you write a number like this, the number of significant figures in this case is actually ambiguous, and that's part of the reason that we're using scientific notation in the first place, right? So this number, as it's written, 150, could actually be 3 significant figures. And if it were 3 significant figures, then we would write it as 1.50 times 10 to the 2 milliliters. Okay, all right. But again, usually when you see a number like this, the safe thing to do is to assume the smaller number of significant figures, and that's what people are usually taught to do. So this would generally be considered the correct answer. Now, if the number 150 milliliters is written this way, here, 150.0, right? Now we know that all of those zeros are significant, and so this number should be written with 4 significant figures. So this is 1.500 times 10 to the 2 milliliters. Okay. All right, 0.0079 pounds. Our number will be 7.9. And then we look at how many spots we have to move the decimal. 1, 2, 3. We have to move the decimal over 3 spots. And this is a number less than 1. So that's 10 to the minus 3 pounds. And then here's the same number again, right? So this is also going to be, this one here, this is also going to be 7.9 times 10 to the minus 3, right? But this last 0 here, right, that 0 doesn't change the value of the number, so the only reason someone would take the trouble to write that 0 is if this 0 here was indeed significant. And if that's the case, then this number has 3 significant figures, and we want to retain 3 significant figures. So we'll write it as 7.90 times 10 to the minus 3 pounds. And our last one, what's that, 50 million volts? This would be 5 times 10 to the, looks like 7, right? 3, 6, 7, yep, 10 to the 7 volts. All right, lovely. Okay, now let's do the same thing in reverse. Take each one of these numbers that are in scientific notation and then rewrite it in standard notation, again, keeping the same number of significant figures. Okay, so pause, work through the problems, then unpause, and we'll compare our results. All right, so 2.61 times 10 to the 4 watts, right? I'll start with 2.61. 10 to the 4 means that it's, since this is a positive number, that means the number is a big number, a number greater than 1. We're going to move the decimal over to the right 4 spots. 1, 2, 3, 4. Right. So this gives us 26,100 watts. Right. If you want to do the intermediate step, you could say this is 2.61 times 10,000, right? The fourth, right? And then just kind of multiply that in your head, or you could even use your calculator if you want. In fact, if you've got your calculator, if you know where the right buttons are, your calculator will convert between standard notation and scientific notation. So you can play around with that too. All right, 9 times 10 to the 6th liters, right? This is going to be 10 to the 6th is a million. So this is 9 times 1 million, or 9 million, right? We could also think about that by just counting how many times we have to move the decimal over. So if we move the decimal over 1, 2, 3, 4, 5, 6 times, right? And that gives us 9 million liters. Right? All right, for the next one, 5.92 times 10 to the minus 5. The exponent here is negative, so that means this number is smaller than 1, and that means we're going to have to move the decimal in the other direction. 5.92, we need to move it over 5 spots. So we go 1, 2, 3, 4, 5. There's our decimal. 1, 2, 3, 4. All right. So this would be, and we always want to put a 0 there to help locate the decimal. If you write it, if you write it that way, it's not really wrong, but it's definitely not the preferred notation. That's much more clear. So we'd write this 0.0000592 grams. And then the last one, that's interesting. Okay, 9.6 times 10 to the minus 4 miles. Oh, wait a minute, I screwed up on the last one too. I wasn't paying attention. I'm sorry about that. But I didn't, I'm sorry. No, I didn't screw up, I just skipped one. Okay, so we did this one right. My stuff started creeping down and I missed it. Okay, so apologize for that. So we got 5.92 times 10 to the minus 5 grams, and then we got 5.920 times 10 to the minus 5 grams. All right, so as we were saying before with decimals, the only reason to put that 0 there is if you measured it, right? Because putting the 0 there doesn't change the value of the number, so the only reason you would put it there is if it was a measured value, if it was part of the precision of the number, or if it was a significant figure. Right? So that means that that 0 is significant, and when we rewrite it, these two are both 10 to the minus 5, so they're the same number, right? But when we write it, in this case, we need to include that extra digit to indicate one more significant figure, right? So this first one here is written with 3 significant figures, and this one here is written with 4 significant figures. All right. Okay. I'm sorry for getting a little confused on that. I'm just writing too big, and my things were kind of sliding down. So I'm going to erase this last one to make a little bit of room. In fact, assuming you've already written it down, I'll erase this one too. All right. So, all right. Good thing is I got another shot, because here's another one. See if I can get this one right. All right, so 9.600 times 10 to the 4th miles, right? 9.600, and it's times 10 to the 4. The 4 is positive, so that means this number is larger than 1, right? So I'm going to move the decimal to the right. I'm going to move it 4 times. 1, 2, 3, 4. Okay, so the number is 96,000. Okay, but if you look over here, the way the number is written, the number is written with 4 significant figures, and I've got a couple of choices here. If I write this 96,000 miles, that's got 2 significant figures, right? If I write it like that. If I put in an explicit decimal place, then that means everything is significant to the decimal place. So that's got 5 significant figures. That's not right either. If I want to write this with 4 significant figures, the only way I can really do it is to write 96,000 and then put a bar over that 0. That bar is a symbol that means that's the last significant figure. People don't use that very often. And the reason they don't use it very often, is because this is so much easier, right? Which is the whole point. That's why we're doing this. All right. Lovely. Lovely. I'm enjoying this. I hope you are too. Okay, another really important thing about significant figures and standard scientific notation is how to do this in your calculator. And every single year I see a lot of people who have problems with this. And so this is really, really important. All right, so let's say we've got a number like 6.37 times 10 to the 9, right? Let's say we've got that number. You want to type that into your calculator. There are a couple of different ways that you can do it. One is you can just type in 6.37 times 10 to the 9. There's a little caret symbol. Oops. The calculator, there's a caret symbol which looks like that. It's like a angular bracket pointing up. And this means raised to the power of whatever you type next. Okay. So the first way that you can do this in your calculator is just to type in 6.37 times 10, 10, and then the caret and 9, right? So that'll be 6.37 times 10 raised to the 9th power. And if you hit equals, you should get the right result there. Okay, it should give you the right answer. But that's a little bit cumbersome using that little caret symbol. Another way that you can do this, oh, I'm sorry, I forgot that I had these guys over here. So if you do that, and then you hit equals, your calculator will display the result, and it may display it in a couple of different ways. It used to be that calculators always displayed them this way with this capital E for exponent, right? And the reason for that is calculators a long time ago used to have this display. There's a certain word for it. I don't remember what it's called. Digital alarm clocks used to have this too. You guys might not even have seen this before, but there were digital displays looked like this, where every single digit was basically an 8. It had 1, 2, 3, 4, 5, 1, 2, 3, 4, had 7 little lines, right, in the shape of an 8. And the way the calculator or alarm clock or whatever displayed digits was just by deciding which of those things it was going to light up and which ones it wasn't going to light up. So in this first one here, if you wanted to make a 6, then the calculator will just not show that line, and it looks like a 6. And if you wanted to make a 3, it would just not show those 2 lines on the left. I messed up. And you get a 3, right? Anyway, so, and calculators couldn't display nice, pretty things like that or that. They can only display things with these perpendicular lines, right? And so, for that reason, calculators back in the day used an E because you can make an E the same way you make the 3, right? You can make the E like that with those little lights. Okay, so some calculators still do that just because that became kind of an accepted way of doing this. I apologize. I keep hitting the wrong button and my little things are popping up. All right. So your calculator might display it like this. It might display it like this with a superscript 09 that doesn't show the 10 in there, and you just have to understand that there's an implied times 10 before that 9. Right? Or your calculator, the newer ones, a lot of them, just because the displays have gotten so much better, will show the number just like that, which is exactly how you would like to see it, right? So my point in that is just when you're using your calculator, know that all three of these things are the same thing. Those all mean the same thing. But just make sure you understand how your calculator is displaying things so that you can read it properly. All right, so now I've inadvertently let the cat out of the bag by displaying the other entry methods here by hitting the wrong button, but that's okay. So this was the first way you could do it with a little caret symbol. The second way you can do it, type this into your calculator, is by typing 6.37 times 10 to the x and then 9. And most of your calculators, if you look on there, they have a 10 to the x key. And so if you got your calculator with you, you might just give it a try right now. Type in 6.37 times 10 to the x, then hit the 9, then hit equals, and it should give you one of those results over there. Now the third one, and this one is really important. I'm going to put a couple of stars and a happy face and even I'm sorry, I can't draw. Even a happy little kitten. The kitten is happy. The kitten is purring, in fact, because someone used their calculator and typed the number in this way. So if you like purring kittens, please try to get comfortable using this notation for your calculator. And the way this notation works is you type into your calculator 6.37 EXP 9. And this EXP button means times 10 to the whatever comes next. So this EXP button does the work of this whole set of digits here, or set of keystrokes, I should say here. And it does the work of the whole set of keystrokes here, right? Some calculators don't have an EXP key. On some of them, it just says E, and on some of them, it says EE, right? But everybody should have on your calculator a key that either says E and capital E, not lowercase e. Lowercase e is something else. Everyone should have on your calculator something that says EXP in capital letters, or E, capital E, or EE in capital letters. So please get your calculator out, look for that button, and try typing this in and making sure that it gives you this result over here. Okay. So the reason that kittens are so happy when people use this last method down here, right, is because using this last method is really, really helpful, and it saves a couple keystrokes, of course, but the real reason to do it is because it actually helps prevent mistakes. And I'll show you what I mean by that. All right, so let's say you've got a problem you need to calculate 4.5 times 10 to the minus 8 divided by 2.3 times 10 to the 5, right? If you use that middle method where you use the 10 to the x key, right, you could type this in as 4.5, right, times 10 to the negative 8, right? You've also got this negative key on your calculator, divided by 2.3 times 10 to the 5. And if you hit the equal sign, you get that result there, right? And the problem is that this result is not correct. And the reason it's not correct is because when you type this into your calculator actually sees 4 different numbers. Your calculator sees 4.5 times 10 to the minus 8 divided by 2.3 times 10 to the 5, right? Or in other words, what your calculator sees is 4.5 times 10 to the minus 8 divided by 2.3 times 10 to the 5. All right. It sees all 4 of these as different numbers, and then it just applies order of operations in order to figure out how to multiply or add them together. And when it does that, it interprets it this way and gives you this incorrect answer. Okay. There are a couple ways that you can fix that. One, and some people will do this, and it's okay. It's not the easiest way to do it, but if your calculator also has parentheses keys. If you use parentheses around these, then the calculator will correctly interpret this as 4.5 times 10 to the minus 8 divided by 2.3 times 10 to the minus 5. So you can use parentheses to fix that, but again, that's kind of cumbersome, and when people use parentheses, again, there's still some tendency to make a mistake. Okay. The easiest way to fix this, the absolute best way to type this into your calculator, is to use that EXP key. So if you type in you type in 4.5 EXP minus 8 divided by 2.3 EXP 5, the wonderful thing about that EXP key is when the calculator sees that key, it interprets this whole thing as one number, and it interprets this whole thing here as one number. And so it automatically is going to interpret this set of keystrokes as meaning that. Without using any parentheses, it's always going to keep that part together and that part together, and that's really important. So if you do that and you hit the equal sign, you'll get that number, 10 to the minus 13, which is correct, right? So you can see in this case, the wrong number is not only wrong, but it's way, way wrong, right? It's off by a factor of 10 to the 10, right? Which is what? 10 billion. It's off by a factor of 10 billion, right? So something as simple as choosing your keystrokes can have a big impact on your results. Right. So you can use your calculator however you want. It's your calculator. You can do whatever feels comfortable to you, but I would encourage you, please get comfortable with this because it'll make your life a lot easier. All right. One other thing I should mention, when we're doing calculations like this, if we go back and look at the numbers that we typed in, the 4.5 has 2 significant figures, the 2.3 has 2 significant figures. So following our multiplication and division rules, the result can have no more significant figures than either of the 2 things that we multiplied together. All right? So that means our result here should have 2 significant figures, right? So we need to cut it off here after the 9, and we're not truncating, we're rounding. So that's going to go from 1.96 up to 2.0. So the correct answer here would actually be 2.0 times 10 to the minus 13. All right. One more comment. Okay. That is metric conversions. Sorry, I got 2 more comments. Okay. One, metric conversions. When you look at the table of metric conversions, you'll see a lot of things that look like this, right? 10 to the 9th. And so when we get into dimensional analysis, you'll be typing in things like this. Okay. The point I wanted to make with this is if you have a number like that in your calculator and you're doing some math with it, right? People very often type this in as 1 divided by 10 to the 9th, right? And this is not correct because this EXP key means times 10 raised to the whatever comes next, right? So this whole thing here then would be interpreted as 10 times 10 to the 9th, which is 10 to the 10th, right? So when you've got a number like this, right, you don't want to type it in as 10 EXP9. Think about this as 10 to the 9th is really equal to 1 times 10 to the 9th, right? So when you're typing that into your calculator, oh, okay. And so if you, I have your answer. If you did this one here, you'd get that incorrect answer. What you want to do is type it in this way as 1 divided by 1 EXP9, right? And that's going to be interpreted as 1 divided by 10 to the 9th. And so that will give you the correct answer here. All right, last thing, sequential multiplication. When you're doing complicated calculations like this, what a lot of people do, and I did this myself for a long time, and to be honest, there's really nothing wrong with it, really. But just to kind of feel comfortable, let's look at this first one here. What I would often do is I would just take all of these numerators and multiply them together, and I'd put in my calculator 26.7 times 1, or if I'm smart, I'd skip the times 1 because we all know that doesn't do anything. 26.7 times 1 times 6.022 EXP 23, and that would give me 1.608 times 10 to the 25, and then I would clear the calculator and I would type in 376.1 times 1, which of course is just going to be 376.1. And then, after I got both of those numbers, I would take the first number and divide it by the second number. And do that, we get 4.28 times 10 to the 22, right? So you can do that. Like I said, there's nothing, it's not wrong, right? Your answer is fine, but it's kind of an extra step and it provides an extra chance for mistakes, right? So what I would encourage you to do is, actually I guess what I would encourage you to do is go ahead and do this, right? Do that, do the math, see what you get, and then try it another way, which is just do the whole thing in one step. So type in 26.7 times 1, or you can skip the 1 because it didn't do anything, right, times 6.022 EXP23, and then divided by 376.1, and then you could say divided by 1, but of course that's not going to do anything. And see what you get from that. Okay. I put 1s in all of these. Maybe I should have left the 1s out when I made this slide. Sometimes making things simple makes it a little bit more confusing. So let's look at the next one. You can, if you want, you can multiply all the numerators together, write down that value, then multiply all the denominators, write down that value, and then take one and divide by the other, right? But you can also just type in your calculator 1.6 EXP3 times 1 times 5.53 EXP negative 9 divided by 422.1 divided by 4 divided by 3.3 times 10 to the minus 5, and give that a shot and see if that gives you 1.59 times 10 to the minus 14. And you can do that whole thing without parentheses. It's just one long string of multiplication and division steps. Okay. Same thing with this one. 2.56 exp minus 6 times 371 times 6.022 exp 23 divided by 4.5 exp 3 divided by 2.57 exp 9, and then if you want, divided by 1, but of course it's not going to do anything, right? And put that in your calculator, see what you get, see if you get 4.95 times 10 minus 5. Right. All right. We should also be cognizant of significant figures. So in this first one, we've got 3 significant figures, 4 significant figures, 4 significant figures. It's not really clear what these ones are, since this is just kind of a made-up calculation. I would assume in this case that these ones are part of a definition. Ones are usually part of a definition, like 12 inches and 1 foot. So I would say that's probably an infinite number of sig figs. So the result should have 3 significant figures, and our result does have 3 significant figures. Right? And our next one, we've got 1.6 times 10 to the minus 3, or 10 to the 3. That's got 2 sig figs. The 1, I would assume that that's some kind of a definition, so that's infinite number of sig figs. This one has 3 sig figs. This has 4. This has 2. So our result should have 2 significant figures. So it should really be 1.6 times 10 minus 14. And on our last one, you can just look through all of those. Again, assuming that this here is part of a definition of some sort. If it's part of a definition, that's an infinite number of significant figures. The smallest number of sig figs is this 4.5, which has 2 significant figures. So we should round this one to 2. This one's kind of interesting because we get 4.95, rounding to 2. If we had 4.949 and we were cutting it off, then it would go to 4.9. If we had 4.951, right, then it would go up to 5.0. When we have exactly, when the part where we're cutting off is exactly 5, it's not always clear whether you should round up or round down. The rule for that is that you should round so that this digit moves to the nearest even digit. So if it's an even digit, you'd keep it the same. If it's an odd digit, you'd round up. That's kind of an obscure rule, and I wouldn't worry too much about it. I would give you credit for this one. If you rounded either up or down, right? I would want to make sure you had 2 significant figures, but so technically the correct answer is 5.0 times 10 to the 5, but I'd give you credit for 4.9 times 10 to the minus 5 also. All right, so in this one, what did we talk about? Scientific notation. Talked about the form, that it's always some number times 10 to the x, and this number is some number between 1 and 10, right? Or above 1 and less than 10, right? Because this first part right here has to be 1 digit, right? 1 digit to the left of the decimal, right? We talked about the reasons for using scientific notation, right? One, that it's just a little bit more efficient, right? Takes up less space, it's easier to read. Also, you end up with fewer mistakes because you're not trying to count zeros all the time, which is really problematic. And most importantly, it makes explicit the number of significant figures. Okay. So you can clearly tell whether a number is supposed to have 2 or 3 or 4 significant figures or whatever. Right. We also talked about how to go back and forth from standard notation to scientific notation, back again, so you should be able to do that. And when you do that, you should be able to do it going back and forth, retaining the same number of significant figures. And we talked about how to use your calculator, and specifically talked about the importance of using that EXP key, or on some calculators, an EE key. Okay. Please locate that button on your calculator and get comfortable using it, because it will make your life a lot better. All right. Thank you very much for sticking with me through this one, and we'll be back again with another video in a little while.